Hello everyone, thank you for coming. As you can see, my name is Ábel Sinkovics. A little bit of history of me. I made a PhD at the Eötvös Loránd University in Hungary, and my research topic was the connection between C++ template metaprogramming and functional programming. So I made quite a bit of template metaprogramming while doing that. I have also built C++ libraries based on or using template metaprogramming. One of them has recently been accepted to Boost. And to make my template metaprogramming work easier, I have searched for and built myself tools supporting C++ template metaprogramming. And over the time, I have realized that such tools that are there for C++ template metaprogramming can be extremely useful when we're using templates the regular way. So the way they were originally designed to build generic data structures and algorithms. So in this talk, I will be looking at the different tools available for such regular usage of templates. So if anyone's after template metaprogramming stuff, then this is not your talk this time. I'm working for Morgan Stanley, and my employer has supported me in giving you this talk. Okay, so let's get started. First of all, what is generic programming? So the title says tools for generic programming. I've searched for a definition of generic programming, and these are the things I've found. If you look at them, you can see that they are both talking about reusability. So that's the common theme among the two. And they also talk about generality and efficiency. So these are the things that matter when we're doing generic programming. And C++ provides templates as a tool for implementing generic data structures and algorithms. So when we decide to use them, either use a library that is a generic library or provides generic components, or to build ones ourselves, then we will have to deal with templates in C++. And this is how template usage typically works. So the programmer writes the code, defining template classes or template functions, instantiating them using templates. He gives the code to the compiler. The compiler compiles it, and if all goes well, then it generates some object code. When there is an error, then it prints out an error report. The programmer can look at the error report, and it can look at the original source code. But the magic is happening here inside the compiler. So based on these two sources, the source code and the error report, the programmer has to basically reconstruct what was going on inside the compiler to understand a non-trivial error message. What he can do about it, well, he has to learn about templates. So this is one of the reasons why the learning curve is a bit steep to get started. But once he understands how templates work, then he can look at the source code, the error report, and then sort of imagine what is going on inside the compiler. So that's, and if the library has been built in a way that it's intuitive to use, then in most cases you don't need to do this. But if something goes wrong, you can easily end up doing such imaginations. Okay, so that was template usage. Well, there are template metaprogrammers and template metaprograms, and they are basically abusing templates in some way to make the compiler do specific things. And if this is what goes on inside the compiler when you're using some sort of a generic library, then this is what is going on inside the compiler when you're doing a template metaprogram. So as you can see that it is way more intensive template usage than the other one. So tools that can make this process doable can be really helpful for the other one as well. So that's the basic idea. What are the tools out there? So here are the two tools that I'll be talking about. One of them is a Clang extension called template, and the other one is Metashell combined with MDB. This is the thing that András Kucsma and myself have been working on, but I'll cover those later. And as I said earlier, the idea is that they can be useful for using generic code and in C++. So what other tools are available? It's not just these template tools. So, I mean, not just these metaprogramming tools. When you have to understand how your generic library works or what is going on inside the compiler, then you've got a number of tools at your disposal, and you had them. We had them for ages. So these template metaprogramming tools are recent, but these other tools have been around for a while. And here are the two new tools as well. So let's start with an example program. This is an artificial example, so it has classes called A, B, C, D, whatever. But you can easily see similar code in real applications as well. So you might have come across such code as well. I have come across such code quite a few times, and I had to do such thing quite a few times. So what you want to figure out is that what is this handle type? You can see that here is a template class A. You instantiate it with int, and it has some sort of a nested type called handle. What is that handle? In a real code, this A could be a type trait, or it could be a container whose value type you want to figure out, or something like that. Well, what's the naive approach? You say that, well, this template class A must be defined in a.hpp, so let's just look at it. So you open that a.hpp, and you can see that, well, yeah, your guess was right. It's defined in that file, but it has no handle, but it inherits publicly from B. So you open up b.hpp as well. And there you can see that here is the handle, but unfortunately, this is just a type alias of something else. And you open that up as well, and you can see that, well, it's another type alias. And you're laughing, but such code can surprisingly easily evolve when you're using templates. So you've got one class. You realize that in an application code that you've got one class, you've got another one. They are almost doing the same. So you create a template class and define the minor differences. And then you've got one level of this hierarchy. You add some type traits to it to make it work with more functions. Then you've got another level, and these things just build up. If you decide to do it manually, and you don't give up at this point, then you can start saying that, okay, here is this C factory instantiated with u colon item. Where does this u come from? Well, it comes from here. So it's du. So you need to figure out what u is, and so on and so forth. You will end up writing notes for yourself that I was looking at this originally, which led me to looking at this. You will be running up and down in this hierarchy. So it's not a nice thing to do, and you obviously need tools. Here is a list of approaches that I will show you, and I will show you how to use these approaches to make this process easier, or to make this first example easier. The first one is, well, you've got a compiler, and you can make the compiler display an error message containing the answer. So you can write your code. Well, you can write your code in a way that it fails to compile. You give it to the compiler. You receive an error report. You can look at the error report, and the idea is that the answer is somewhere in the error report. This is one of the things that tend to come into people's mind the first time when they decide to use some tools for resolving such things. And you can either write the code yourself to make the compilation fail, or you can use existing ones, such as boost MPL print. This is how you can use it. You instantiate it with the type you want to know more about. And here is an example output or error report from Clang. There is the answer. You might write a script if you need to do it often that just grabs that specific part out of an error message. Here is another error report from Visual C++. Note that here the answer is in two pieces, so you need to put it together, but this is still much easier than the original manual approach. Another tool is metamonad's fail with type. You can use it in a similar way, and it works in a similar way. Well, what makes it a bit easier to use is that there are these tons of underscores around the answer. So when you're looking at a long error report, you can spot it easier. Here is a Clang output. The response is there. And here is a Visual C++ output. And here, the response is at one place. But this is specific to the way Visual C++ is doing the error reporting. Another approach is that you can display the name of the type at runtime. So basically, you write the code that compiles, and this is a special code. So it's not your real application code. It's a small special piece of code. You give it to the compiler. It generates some object code. You link it, and you run it, and it prints out the answer to the standard output. So that's the idea. For this, of course, you need to create a temporary small executable that does it for you. So to look at one type, you need to do some extra work to get it done. Well, the most straightforward way of doing this is using the standard type ID. If you do it with GCC or Clang, this is what you get. This might look scary, but it's just a mangled name. So there is a utility that can demangle it for you, and then you get the answer. If you're using Visual C++, then you get the right answer right away. If you don't want to use an external utility with Clang or GCC, then you can use the Boost type index library, which can be used in a similar way. You instantiate type ID with CVR with the type in question. You call pretty name on it, and it will print gint for you. So it will do the demangling of the type name as well. In Visual C++, it will print class gint, but so you get basically you get the answer. You can use IDs as well. The IDs I tried and I used to know before coming here were or did all behave the same. You could load the code in the IDE. You can tell the IDE what you're interested in. You usually tell it the IDE in a way that you right-click on this inside the IDE. Well, assuming that this is a graphical one, which today most of them are graphical. And then you click go to declaration or go to definition. And then it has a compiler, at least a parser of the compiler in it, and it will take you here. There you go, here is the definition. But it's not that useful in this case. If anyone who has been to the Templator presentation, then you know that there are better tools out there. If you haven't been, just search for it or watch the video. There is a tool that can do much better than this. So it's an IDE which can give you the right answer as well. You might have not known that you can also use GDB for getting this information. It might look strange because GDB is a runtime debugger, and this time you're about to use it for compile time debugging. What you can do is that you get your source code, you compile it, you generate the object code with debug information. You link it, you load it in GDB, and basically GDB will tell you the answer. And this is how. So you compile the code with debug information, you start it in GDB, you get the GDB prompt, and then you set a breakpoint inside your main function. And it's not the main function that's important, but in that scope, there is a variable of type a int handle. So there is a variable of the type in question. And GDB will tell you that, okay, there is your breakpoint, you run the execution, it stops, and then you can ask GDB, okay, what is the type of X? And GDB will tell you, well, it's gint. And not only will it tell you that it's gint, but it will also show you the entire instantiated template class. So it can be pretty useful. So these were the sort of tools that have been around anyway. Here are the relatively new ones. One of them is Metashell, which is basically a template metaprogramming shell. So as I said earlier, it was built for template metaprogrammers. This is how it works. You run the shell, You take your source code, basically you include your source code into the shell, and you ask the shell what you're interested in, and the shell runs a compiler, or at least a parser of it, and then it tells you the answer based on that. So here is how you can use it. You start Metashell from the, it's a command line utility. It's basically a REPL shell for template metaprogramming. You can say include my main CPP, and then you can ask the question, and it will just tell you, well, it's gint. That's it. Okay. Are there any questions so far? Yes.
Do you have instantiate a int and you made that to see what's notes?
I'm sorry, I couldn't hear.
In this example, do you have to have a int in your main that's
okay, so do I need a.int, this part in the CPP, right? That was the question. Well, you don't need to have it, so you can include only the a.hpp. And then inside the shell, so when you're asking the shell, what is this, then that will instantiate it.
Does Metashell work on Windows?
The question was if Metashell works on Windows, and yes, it works on OS X, Windows, and Linux as well.
Which compiler does it?
It uses Clang on all platforms, a patched version of Clang. So the question was which compiler it uses, and it uses Clang. There is also an online demo of Metashell, so you can run Metashell from a browser. If you search for Metashell, or if you go to that website, then there is a link to the online demo. And then you can try it from your browser. Are there other questions before we move on? Okay. So this was a first example, the most simple I could think of. Here is a little bit more complicated. So you've got a template function. This can be an implementation of a generic algorithm. Let's call it fun for now. And you instantiate it with some type. And the question is the same. What is the type of this thing? And there are the same tools. And they work mostly the same. So you can use boostmpl print, for example. When you use that, then you should put boostmpl print inside your template function. So when your template function is instantiated, then the printing will be triggered. And this is the output you get. There is the answer. This is the Visual C++ output, and there is the answer. So the output is basically the same as it was before. You can use metamonad's fail with type in the same way as well. You put it inside your template function, and then this is the output you get with GCC. There is the answer. This is the output with Clang. There is the answer. And this is the output with Visual C++. There is the answer. Okay. IDEs. Well, this gets more tricky with IDEs than the previous one, because when you right-click on that, so you say that, okay, this is what I'm interested in, then this might mean that this is fun instantiated with int, or double, or bar, or whatever type. So when you click at that point or place in your source code, then it can refer to a virtually infinite number of functions. And you should relate it to that place. And again, if you've been to the Templar talk, then you know that they have solved this problem. Okay, GDB. You can use GDB as well. You can compile your code with debug information, load it in GDB, and set a breakpoint inside the template function. And then you can just run the execution, and when you hit the breakpoint, then GDB will tell you which instantiation of your template function you are in. So you can keep trying until you reach the instantiation you are interested in, and then you can ask for the type of this thing, and you get the same output as in the previous example. You can use Metashell as well. You can load your source code into the shell and ask the question. Note that you have to tell Metashell that you're interested in doubles. So if you go back to the code of your function, you need to resolve this T yourself if you're using Metashell. You might need to do it with another query before. So you might need to run queries before in Metashell to figure out what that is, and then ask Metashell this answer. So this is sort of a disadvantage. But you get the answer. You might ask, okay, why is it Gin? So, okay, this is what it refers to, but how did the compiler get there? If you recall those arrows and red lines in your imagination inside the compiler, you might be interested in how that worked, how that happened. So what was basically going on inside the compiler? And what Metashell provides you is a utility called MDB, which is a compile time debugger or template debugger. You can load this expression inside MDB, and it is a debugger inspired by GDB. So you get a similar interface, and you can ask for a forward trace, which is similar to the back trace, but this debugger sort of magically knows the future. It makes use of the fact that template metaprogramming is pure, so it pre-calculates everything and pretends that it is knowing the future. So what will happen after your current location. So you can not only ask for a back trace, but you can ask for a forward trace. And a forward trace itself is what will be instantiated from this point. And then it will show you that A will instantiate B, C, D, and so on and so forth. So it can show you the instantiation tree, which can be useful. Other questions before we move on? Okay. Here is another example. Well, the question is, what is the type of T when you instantiate this template function with F or with D? So here is a universal reference, and what will it refer to, or how will it be used in the compiler? Scott Meyers' book in item 4 lists a number of tools you can use to get this answer. Metashell is also one. So you can use Metashell to learn this information or to find this out or just to play with it. You can either include this source code into Metashell, or you can just define your template function inside the shell as well, whichever is more convenient. And then you can start playing with it. You can say, okay, I want to know how it is deduced when I instantiate it with this number. And then you start up a debugger, you ask for a forward tree, and there is your answer. But in this case, T was deduced to be double. And then you can quit the debugger and try again. So you can define a local variable and then try to instantiate it using the local variable as well. And then ask for the forward trace, and here is your answer this time. So as you can see that you can make quick iterations, so you can quickly try different things and approaches out, which can be convenient when you want to learn about how these things work and what is going on. So when you end up doing these kind of things is that when you get a piece of code, it doesn't compile, or it doesn't compile the way you want it, so you want to learn what's going on there. And in such situations, this can be pretty useful. So far, from the template metaprogramming tools, I've shown you Metashell and MDB. There is also a Clang extension called Template. It was originally developed by people from the Eötvös Loránd University in Hungary, and then it was forked by Michael Persson, and he made some cleanup to it and added very useful features to it. So today I will show you this fork of Template. And it is basically a drop-in replacement of Clang itself. It has some specific or template-specific arguments, such as profiler or safe mode. Otherwise, you can just run it instead of Clang. And it will give you a trace file, which is a protobuffer file. And then you get a template convert utility, which can convert it to some format that you can easily consume. So you can get an XML report or a GraphML, GraphWiz, or a CaCache Grind output. And what this trace contains is basically which templates were instantiated by compiling your source code, in which order, how they triggered recursive instantiations, and it also contains profiling information if you ask for it. So here, let's take a closer look at the call grind output. So basically it generates a call grind dump, which contains information about runtime call trees. But in this case, the runtime calls will be templates instantiating each other. So when the call grind tools think of functions calling each other, in this trace, there will be template functions and template classes instantiating each other recursively. But if you, question?
What's the meaning of C time here?
The question was what the meaning of C time is. That's the profiling information. So this trace contains information about how long it took to instantiate different templates. So if you want to profile your source code, then it will give you the answers. Other questions? Okay. So there are utilities like KCache Grind, I don't really know how to pronounce it. But these are GUIs which you can open, or you can open the dump with, and then it will show you useful things, such as this annotated source code. This is the original source code of your source file, and there are extra entries about the template instantiation. So it talks about functions calls, but one calls to F means that F template was instantiated once. Okay. You might want to get a better understanding of what is going on inside template instantiations.
Sorry, question.
Yeah.
So can you do anything if the compile actually doesn't work? I mean, that's the whole problem. If you're trying to...
I will get to that later. So the question was, what happens if the compilation fails? And I'll get to that later. So far, we assume that everything, at least it compiles. And we will get to compilation errors later. Yes, it's an important topic. And yes, that's the most useful part. Yeah, not always, but in most cases. Are there other questions? Okay, so you might want to get a better understanding of what is going on inside or during the compilation. I've already shown you MDB. Here is another tool, or at least another example. Here is a variadic template implementation for summarizing numbers. If this is what you want to do, this is probably not the implementation you should be using. But this was the most simple variadic template instantiation I could think of, so that's why I was using this example. Here is an example usage. It instantiates it with ints only, and it is trying to summarize 10 ints, basically. And what we're interested in is, okay, what templates are instantiated by this specific expression. And you can load this HPP in Metashell, and Metashell provides a utility called instantiate expression. And then you can tell it, okay, instantiate this expression. And instantiating an expression means instantiate all templates, or do all template instantiations triggered by this expression. And then it will, well, in the normal shell, it will just tell you, well, okay, I did that. So, or you can tell that there was no error. But if you do the same in the template debugger, then you can ask for a forward trace, and then you can see the template instantiation tree. So you can see what you usually think of that, okay, it instantiates it with 10 ints, and then with 9 ints, and so on. So you can look at these things, either to learn or to debug. And so far I've shown you artificial examples. Let's look at a concrete one. What happens when you instantiate or when you call the default constructor of a standard string? So can anyone tell me who's not a STL developer?
Basic string of char. Basic string of allocator char trace.
So that was 2 so far.
The basic string itself.
That was 1. Basic string and allocator.
Char trace.
Char trace, okay. So 3. Any other guesses?
Iterator traits.
Iterator traits, okay.
Allocator traits.
That was, we had that so far. So 4 so far. Any other guess? Okay.
Locale.
local. I don't know who said that, but I heard a local from there. That's 5 so far. Any other guess?
We leave it a lot.
Okay, let's look at it in MDB. Start a Metashell, get the instantiate expression utility, get string, and instantiate the expression calling the empty or the default constructor of string. Load it in the debugger and well, let me point out that it's not all the template instantiations. So this tool shows you the memorizations as well. And unfortunately, I couldn't increase the font size, otherwise it wouldn't fit on the screen. But I can show you a hint using color highlights. The white ones are just memorizations. The yellow one is a utility used by the instantiate expression tool, and the red ones are the template instantiation, are the real template instantiations. So there is 1, 2, 3, 4, 5, 6, 7. And I leave it as homework once you get the slides to look at them in detail. But the point here is that once you have such utilities and you've got a generic library, then you can use it to look at different aspects of the generic library and to understand how it works really. I mean, you probably have an idea of how it works, but using these tools you can validate it as well. Okay, you might also be interested in compilation speed. So if you're working on code that's using templates heavily, then after a while you probably end up saying, compilation is too slow. What can I do about it? I want to make it faster. And to optimize compilation times, you need to measure it first. And here are tools you can measure it with, or profile it with, basically. I will be using a boost graph example for this. So in the boost graph examples, there is one called A*cities. And if you try to compile it with Clang, you can see that it takes more than 3 seconds, or at least on my laptop, it took more than 3 seconds to compile. But if you use template and you provide you build the call grind output, then you can open it in KCache Grind and you can get a graph view. And this is basically the template instantiation graph. So you can see all the templates instantiated using during the compilation, and it has the profiling information in it as well. So these percentages tell you how much % of the time was spent on instantiating that specific part of the tree. And it is talking about the subtree underneath. So you can go into depth on these branches you're interested in.
So is the time spent there based on compiler CPU time or number of template instantiations?
The question was if it's number of template instantiations or CPU time. The answer is CPU time. Well, it's the time of the box, so the clock is queried. Are there other questions?
Curious if the coloring, what's the key to the color?
Question was what the key to the color is, and my answer is I don't know. It's added by the GUI, so I don't know.
Is there a way to use these tools to, for example, if I create template expressions, enable them, say some types, find out what types were actually created, were given to such a class, a certain class was not instantiated. Is there a way to do that?
I'm not sure I
Enable
understand.
if some expression, those sort of things. So was this, so enable if something or something else. So what was the type actually assigned to the class? Is there a
So
way
the
to do
question is, can you look at into enable if?
that? Right, or other such expressions.
Well, so in my understanding, the question was if you can look into enable if for other Sphinx expressions.
What was the result actually that was passed to the program that was generated?
So when you're doing Sphinx, then you get template instantiations. I mean, the compiler instantiates templates. So they should, I haven't done that so far, but they should appear because in Clang, when it starts to instantiate a template, then it loads that entry. So So in theory, it should appear in the output, but you need to try.
Does it change at all for if you turn on, or how does it change for compiler optimizations?
The question was how it changes for compiler optimizations. I haven't done profiling with compiler optimization so far, but given that even if your compiler is optimizing, it still has to instantiate all templates it would otherwise instantiate.
So the relative relationships are probably the same.
So I would expect the same or a very similar template instantiation graph, but based on my other earlier measurements, when you turn on optimization in the compiler, then compilation time gets faster or quicker. That is what I have measured with other template programs.
The topmost value, 56%, is that the percentage of the overall compilation time, or just for this template instantiation tree among, the template instantiation steps?
Based on my understanding, that's the overall
It's switchable in the GUI.
percent of that part of the tree.
Okay.
I believe for template you only show the graph of all the types that were finally instantiated, right? If you go through SFINA and you go through like a few of them, and then it fails errors out at some deep nested level, that whole tree is discarded. That's what I'm understanding.
So the comment was that if template or SFINA fails, then the whole tree is discarded.
Mainly a part of the tree.
And the implementation of this Clang patch works in a way that when Clang starts to instantiate a template, then it prints out a log about it, and then logs are never removed. So even if it turns out to be a bad pass, then it's already outputted. But as I said, I haven't tried it. This is my understanding of the implementation. Are there other questions? Okay, so we can move on. If you look at the source code with the template instantiations inside it, so this is again the Boost example program, then you can see the profiling information there as well. Okay. If you are optimizing compilation time and trying to reduce the number of templates instantiated, then you often ask the question, okay, it is often useful to get a list of all templates instantiated during building your source code. So basically a textual list saying that template foo was instantiated with int, template foo was instantiated with double, and so on and so forth. So you can make statistics on it, or you can search for it, or you can process it. And there is a text output of template, which gives you an output that you can use. You can do some grep and set on it, and then you can easily get this list. And then once you have this output, then you can make statistics of this. So it can be pretty useful. It's pretty simple, but still it can be extremely useful because it can stand out, okay, here is a template that I instantiate 1,000 times. And I didn't really think about that it might be instantiated. So this kind of information can stand out with this. Other questions so far before we move on to errors? Okay. In that case, so far we have assumed, as I said earlier, that your code compiles. But in many cases, and those are the cases when you need these tools the most, your code does not compile. And yeah?
Sorry, going back to the previous slide, so how do we use this to speed up compilation time?
Well, this will not speed up your compilation time. It helps you get a better understanding of what gets instantiated.
Okay.
So if you've got a compilation unit using templates heavily, and you get an extremely large tree with thousands or maybe even more nodes, tens of thousands of template instantiations, then you need to do statistics. And you might say, okay, let me get a number of the templates that were instantiated the most. And then things can. So it's basically about making statistics about template instantiations.
You might be instantiating things you don't expect. For instance, int unsigned, so you can eliminate one of them and stuff like that.
comment was that you might instantiate things that you don't expect, and this way you can find them and get rid of them. Are there other questions or comments? Okay. So in case of errors, what you basically need to do is to debug the compilation process, a failing compilation, so a broken compilation process. And here is again an example, an artificial example program, but I think it is a relatively often used example that you've got a person class, you've got a vector of persons called people, you try to sort it, and of course there is no comparison for the persons, so you get an error message. This is what you get from GCC. It is GCC 4.8, so it's a recent compiler, relatively recent compiler, and it is this long. And of course, the answer to the question is there. You might want to understand how it got there, basically. Of course, concepts are coming which will lead to better error messages, but even then, or until then, you need to understand how it got there. So you basically want to get an information about, okay, how did it get from the instantiation of sort to the comparison of persons. And the standard template library is a library we all know, so we probably, or most people probably knows the answer, more or less, that how this happens. But if you have to deal with templates in an application code that you're looking at the first time, or it is at a part of your application that you rarely deal with, it might not be that trivial or self-explanatory that how did it get there. So what is going on during template instantiations. And what you can do based on this error message is to open that header file up, and then you can see, well, there is the comparison, and it happens in a template function called heap select. So what you can do to get an insight to this is that you can take your CPP file, start Metashell, include your source code into Metashell, and run into this problem that you're including a piece of code into your shell that fails to compile. So Metashell will display the error message to you, and then it will not include your source code. And then you will say, oh, I forgot it again, because you will forget it all the time. That what you can do about it is you can comment out the parts of the source code temporarily, the parts of the source code that caused the error, the compilation error. So in my experience, it is usually not the code that starts the template instantiation chain where the bug is. So commenting that out and then including it into Metashell is a useful thing, and then you can start debugging. And in some cases, I need to comment most of the source code out, or I just include some headers from the top of the source code or do something like that. So this is the most troublesome part of getting to the debug environment. Once this is done, you can include person CPP, and then you can get this instantiate expression utility, and you're outside of the scope of the main function. So the expression that caused the problem is inside the main function, but in the shell you're outside of the main function. So all the local variables that you need for this expression, you need to define in the shell as well. And once you have all the local variables you need, you can start this expression inside the template debugger. And what you can do is that in the original error message, and you will have it on the screen because you will forget to comment out the breaking parts all the time, it will tell you the location of the source code where it broke. So you can open that source file up and look at that. It is the heap select template function that was causing the problem. So inside your template debugger, you can set a breakpoint saying that, okay, stop the compilation when it reaches the heap select template function. And then MDB will tell you that, okay, breakpoint is created. And since MDB knows the future, it can also tell you that, and you will hit this 2 times during your compilation. And then you can start the execution of the metaprogram and then hit the breakpoint. And when you hit the breakpoint, you can ask for a backtrace. And it will give you a backtrace similar to the backtrace you get from a runtime program in GDB. And it will contain, so the stack frames will be the templates instantiated, the template classes and the template functions. So it will show you that you started with sort, which instantiated intro sort loop, which instantiated partial sort, which instantiated heap select, and here are the template arguments as well, if you need them. So with this debugger, you can step forward and backward in the template instantiation process to get an understanding of what's going on. You can ask for back traces. As you have seen earlier, you can ask for forward traces as well. And most of the tools basically all of the metaprogramming tools I've shown you are all dependent on this template utility. And the template utility is dependent on a Clang patch, which is not in Clang yet. So if you want to get it, well, for Metashell, there is a binary installer for a number of platforms, including a number of Linux distributions, OS X, and Windows as well. If you want to build it from source, you need to check out Clang, patch it, and then you can get the template. But it is so there is a pull request for it to be merged into Clang, but it's not accepted yet due to the lack of tests for it. So in summary, I have shown you that which tools you can use to debug template usage in your application. And by template usage, I refer to regular template usage. So using templates the way they were meant to be used, implementing generic algorithms and data structures. And I've shown you tools that have been around and can be useful to get a better understanding of how these templates work inside. And there are a number of template metaprogramming. So tools built for template metaprogrammers that can be extremely useful and give you insight into the template instantiation process. So thank you for your attention. And do you have further questions?
Just quickly, on Windows, you were saying Metashell exists, but MDB doesn't unless you have a patched version of Clang.
And so the question was, Metashell exists in Windows, but MDB does not. MDB is a part of Metashell. So Metashell has everything exists on Windows, basically.
But you need the Clang patch.
If you download the binary installer of Metashell, you get MDB and Metashell and templated all together.
Oh, it comes as a thing.
But if you decide to build it from source because you want the latest yet unreleased version, then you need the Clang patch. Yeah.
I have a question. So there is one type of problem specifically, which it's the ones that I found most annoying to debug, which is when you have a function with a decal type, return type, and this depends on other functions that are as well decal type, return type, and so on and so on and so on, such that when you get an error, actually you get the error that simply this function is disabled because the expression doesn't compile, but then it's really hard to know like where in the tree of expressions actually something is missing. And I wonder if like with this you can also debug these decal type expressions.
So the question was if you get a function with a decal type return type and which instantiates further templates, and in that instantiation chain there is an error, then that function is disabled, or that overload is disabled, and how can you debug it, or how can you debug it? So you can try loading it in either Metashell and look at it with MDB, or create a dump or generate a dump of it with template and look at it with KCache Grind.
And will it tell me like what inside the expression failed to?
So the question was, will it show what failed? And I say it should, even though I haven't debugged such a thing yet. But it should.
So the binary distribution of the Metashell will include the template.
So the question was if the binary distribution of Metashell includes the template, and yes, it includes the template as well. but it will usually install it in a way that you cannot easily start it. So it will be installed inside a Metashell directory to avoid it interfering with other compilers. So you need to look deeper if you want it, but you can use that as well.
How does debugging finite work? Imagine I'm implementing a library and it's not picking the right one, and I want to know why.
So the question was how to debug Spinny, and as I said earlier, it should display all the template instantiations triggered by the compiler trying to do this, and then you should be able to look at it. But as I said, I haven't debugged Spinny related issues.
Yeah, but I'll instantiate all of them. I want to know why it's dropping this one.
So the question was, it will instantiate all of them, and you want to know why it's broken. It should lead you to the place where it stopped. So it will show you the instantiation hierarchy.
Okay.
And that should lead you to the
I
answer.
guess I need to play with it. Thank you.
Are there other questions? In that case, thank you for your attention.